This is a short presentation of an application of using binary numbers and formatting a letter in a word processor. Hopefully, after you have gone through this presentation, you will see how what you have learned is applied to the creation of software programs. The letter we will be using as an example is the letter R. And what is the letter R in binary? Compliments of Wikipedia, there is a chart that shows the binary equivalence of a large number of characters. So if we look for the letter R, and then we move over to the left, we will see under the B1, B2, B3, and B4, those are the first 4 bits for the letter R, which happen to be 0, 1, 0, 0. So let's move those up under our chart above. The next set of bits for the letter R can be found above it, bits 5, 6, and 7. As you can see here, it is a 1, 0, 1. So we'll move those up into our chart. Now if you look at the total binary string, what you see is that it is the number 82. So the number 82 represents the letter R to a computer. Now that we have the binary for the letter R, let's figure out how we want to handle the formatting of it. We can do this by setting up our own number scheme using 8-bit binary values. I've created a chart below that will represent our formatting options and their associated values. If the value is 0, it will just have a normal formatting. The number 1 will represent bold, the number 2 italics, and so on. Notice above that the 64 and 128 values are not being used, so we'll just call them unassigned for now. If we ever want to upgrade our word processor capabilities later and add more formatting options, we could utilize these 2 bits to represent those options. So, just to make things clear, let's make a new formatting chart in our normal binary charting method. Now, if we wanted to have a character that has no formatting, based upon the chart that we have, it would have a decimal value of 0, which would mean all zeros in our binary chart. If we were looking to have bold formatting on the character, it would have a decimal value of 1, which would mean that we would turn on the 1 bit to get it to be bold. If we want both bold and underlined, that decimal value would be 5, which is the 4 plus 1. So we would turn on the 1 bit and the 4 bit. And if we wanted bold, underlined, and superscripted, the value of that would be 21, which means that we would turn on the 16 bit, the 4 bit, and the 1 bit. So now that we know how to establish a set of formatting based upon binary numbers, one thing that we may want to do is to be able to look at a format or a letter and determine whether or not it is bold, or determine whether or not it is underlined, or if it is superscript. We're going to talk a little bit now about how we would do that. If I said, what is 5 and 4, you'd probably say, what? Or you'd add them together and tell me the answer is 9. In binary, though, the answer would be true. Weren't expecting that, were you? Let me explain. When we AND 2 numbers, we are asking whether or not the first value has the second value as one of its ON bits. So to make a 5 in binary, we turn on the 1 bit and the 4 bit. Therefore, it is true that 4 is on in the number 5. If I said 5 and 2, the answer would be false. Why? Because the 2-bit is not on when we create the number 5. And by not on, again, I mean it is a 0. To apply this to our word processor, we could look at some binary values and ask a question such as, is this character underlined? Using the example from the previous slide, underline is the number 4. So if we looked at the following binary strings that represent formats in our example, we would really ask if their values had the 4-bit turned on, or is the value and 4. So again, here is our chart showing the binary values and their corresponding formatting. The 3 rows you see below are the values from the previous slide. So in the first line you'll see that the only formatting we have is bold, which means that the 1-bit is turned on. So if I said 1 and 4, the answer would be false. 4 is not one of the bits turned on to make the number 1. If I said 5 and 4, it would be true, which means that it is underlined, because 4 is one of the bits turned on to make the number 5. And then in the third line, which is 21, I would say 21 and 4 is true, because the 4-bit is turned on to make the number 21. Therefore, so, if we programmed our word processor to read the first 8 bits to get the letter, then the next 8 bits to get the formatting of the letter, we would have what we need to describe the letter. The first 8 bits are the letter R. The second 8 bits are the formatting of the letter. Let's say bold and underline in this case. And if we wanted to add a size capability, like the point size of the font, we could have the program read the next 8 bits as the size, where the binary value equals the number of points of text size. In this example, you could see that's the number 12, which would be 12-point text. Do you see it? So in our example, our computer would read the 24 bits above and would recognize that we have a 12-point bold and underlined letter R. Is that cool or what? And that is it. Hopefully this has illustrated how the binary system is very suitable for the computing environment, and how understanding of the binary system helps unlock a little bit of how the computer works, and helps to demystify some of those things that we all just assume is some kind of magic that takes place inside the computer.